Hey there, the goal of this presentation today is talk about metabolism of lipids. In particular, talking about triglycerides. These are the lipids that we are eating, and the short for triglycerides is TAGs. So triglycerides. So the triglyceride, again, is a glycerol backbone with 3 carbons, and then long fatty acid chains like this. Those fatty acid chains can be saturated or unsaturated, depending on the source of the fats and oils we're eating, as to tell us what triglycerides are going into our body. So the pathway that involves the breakdown of triglycerides to obtain energy starts with the hydrolysis of the triglycerides, the cleaving, the hydrolysis into the 3 fatty acids and glycerol. From here, the fatty acids undergo a process called beta-oxidation. And beta-oxidation involves, we have our fatty acids here that are composed of hydrocarbon chains, 2 carbons at a time. The fatty acid chains get sliced into 2 carbons at a time and get converted into acetyl-CoA. From this pathway, the acetyl-CoA can enter the citric acid cycle and the electron transport chain to give us oxidative phosphorylation and ATP. If we are under some extreme starvation, we are producing a lot of this, more than what the citric acid cycle needs, and we can get some spillover into this acetyl-CoA, turning into some ketone bodies. Or this acetyl-CoA can contribute in protein metabolism or the production of steroids, which we're not really focusing on here. So another thing that can happen is if we are taking in a lot of fats and they get synthesized and we get too much acetyl-CoA, it can turn back into fatty acids. That fatty acid combine with some glycerol to turn back into fat in your body. So I don't really like this diagram too much. I am going to probably get rid of my ink on here right now. Oh, I said keep. Let's try this again. Oh, it's going to keep it. Darn it. That's okay. So fatty acids have 2 fates. They can, if energy is in good supply, they can be converted back to triglycerides and stored as adipose. When cells need energy, the fatty acids get transferred to acetyl groups of the acetyl-CoA. So let's go back to this diagram. Fatty acids have 2 fates. They can get turned into the acetyl-CoA for energy, or they can get turned back into triglycerides and stored as fat. The glycerol has 3 options. It can undergo conversion for glycolysis and turn into energy. It can turn into new glucose, or it can be part of that triglyceride resynthesis. Now, for this, I'm going to go to the drawing that I drew right here, and let's just follow this pathway. So we're actually starting right here. So we're starting with fats. Fats can get broken down into glycerol and fatty acids. This glycerol and this fatty acid, if energy is in really good supply, can come back together to form triglycerides or TAGs, and it gets stored as adipose. That's called lipogenesis. Lip is for fat, genesis is to make new fat. The glycerol can also be converted into pyruvate and enter this pathway to get energy. All right, so those were two of the three fates. We could turn it back, the glycerol back into triglycerides as adipose, or it could be converted to pyruvate and we can turn that into energy. If for some reason our body is in short supply of glucose, it goes to the fats to get that glucose, and this is where it comes from. The fats break down to form glycerol. The glycerol turns into pyruvate. The pyruvate turns into the glucose. Glucose is the preferred energy. So not only can our glucose now follow the pathway for energy production, the fatty acids can also enter through beta oxidation. The fatty acids can be broken down 2 carbons at a time into acetyl-CoA, where it enters the citric acid cycle, produces the high energy carriers, which give off their electrons, which results in oxidative phosphorylation to turn ADP into ATP. So the fatty acids can be turned into acetyl-CoA. Now, if we have too much acetyl-CoA, our acetyl-CoA can be turned back into fatty acids. So that's called fatty acid synthesis. So this arrow is going both ways. We have the fatty acids turning into acetyl-CoA, and if the abundance of this is pretty high, the acetyl-CoA can get turned back into fatty acids, which can combine into glycerol and turn back into fat. So another thing that I included here is that if we take our glycerol and turn it into pyruvate and turn it into glucose through gluconeogenesis, that glucose can then be stored as glycogen, glycogenesis, the creation of new glycogen. And if we need to go to that glycogen store, we can break the glycogen down and using glycogenolysis to get our glucose back. So this is just a summary of the beta oxidation pathway, and it's more in detail than what we really need here. But the important thing is that it catabolizes the fatty acid by removing atoms 2 at a time. So I have that here. Fatty acids get broken down through beta oxidation, 2 carbons at a time, and it gets converted into acetyl-CoA. So what happens with extreme starvation? I heard a weird noise. So the preferred fuel for our body is glucose. So we start with glucose and it turns into pyruvate. We get our ATP from our glucose. Now our glucose levels have gone down. So when our glucose levels go down, when all of the glucose in our blood gets used up for ATP synthesis, the body goes to its glycogen. So all the glucose is used up. We go to the glycogen. We reach the glycogen and we break the glycogen down and turn that into some more glucose. So that's given us some more glucose. When all of the glycogen is used up, the body goes to the stored fat. And at that point, We've used up all of our glycogen. We've used up all of our glucose. We need to make some more glucose because our brain prefers using that as fuel. So it starts to break down our fats. And it breaks the fats down into glycerol and fatty acids. So we use up all of our glucose, we use up all of our glycogen, we start to break our fat down. Now the glycerol can be turned back into pyruvate and form glucose or enter the citric acid cycle. So our glycerol can turn back into glucose or it can head in this direction. Each fatty acid undergoes beta oxidation, 2 carbons at a time. Here we have our beta oxidation, which is making acetyl-CoA. Now, the problem with this is when we are under extreme starvation, our body starts putting this beta oxidation into overdrive. And it starts taking our fatty acids and just like turning into lots and lots and lots of acetyl-CoA. Far more than what this cycle needs. So we start to get a buildup of acetyl-CoA. So this makes a lot of acetyl-CoA, much more than the citric acid cycle can handle. What happens is that the excess acetyl-CoA will get converted to ketone bodies, which can build up in the plasma of our cells. So under severe starvation, excess acetyl coenzyme A produced production from beta oxidation produces more acetyl A than the citric acid cycle can handle. The extra acetyl CoA gets converted to ketone bodies, and that gets concentrated in the plasma. Ketone bodies can also be used as brain fuel. So there's some function in the ketone bodies being produced. However, ketone bodies can build up to dangerous levels in severe situations. So this concludes my discussion of fat catabolism and anabolism. We can break down fat into glycerol and fatty acids. That glycerol can be further broken down and be turned into energy. Fatty acids can be broken down and turned into energy. The fatty acids can be broken down and turn into acetyl-CoA, which can turn into ketone bodies if there's too much of it. The glycerol can be turned into glucose, which can be turned back into glycogen through gluconeogenesis, or the glycerol can be turned into glucose through gluconeogenesis and can be turned into glycogen. So there is a lot of flux happening in our body at any given time. A lot of times, if we're eating too many fats, our body just breaks it down and then puts it back together, and it gets stored as adipose. So I hope that you have learned something about fat metabolism. Thanks for watching. Have a great day.